In the quiet hours before dawn, there exists a particular kind of silence. The world holds its breath between darkness and light, between yesterday and tomorrow. But on certain mornings in the 1960s, that silence shattered with a violence that rattled windows, cracked plaster, and sent shockwaves rippling through the very foundations of American homes. This was the sound of the future arriving whether people wanted it or not. This was the sonic boom. The story of the sonic boom is inseparable from one of the most ambitious technological programs of the Cold War era. It represents a moment when human ingenuity pushed against the barriers of physics, when political will collided with public tolerance, and when the dream of supersonic passenger travel seemed both inevitable and impossibly close. The research conducted during this period would generate more than 100,000 recorded sonic booms, produce hundreds of technical reports, mobilize the nation's brightest aeronautical minds, and ultimately reveal truths about the relationship between technology and society that we're still grappling with today. This is the story of NASA's sonic boom research during the supersonic transport era, a tale that encompasses wind tunnels and computer programs, test pilots and theoretical physicists, military bombers repurposed for civilian research, and an entire city subjected to a controversial 6-month experiment. It's a story of remarkable scientific progress achieved in service of a dream that would not be realized, at least not in the way its proponents had envisioned. The rapid advancement in understanding sonic booms during the 1960s emerged from an unprecedented synergy among multiple disciplines and institutions. Flight testing provided real-world data that could be compared against wind tunnel experiments. Psychoacoustical studies measured how humans actually perceived and reacted to these unusual sounds. Theoretical refinements gave researchers the mathematical tools to predict and potentially control boom characteristics, and powerful new computing capabilities allowed for calculations and simulations that would have been impossible just years earlier. What made this progress possible was something relatively rare in scientific endeavors: the largely free exchange of information among NASA, the Federal Aviation Administration, the United States Air Force, airplane manufacturers, academic institutions, and professional organizations like the American Institute of Aeronautics and Astronautics and the Acoustical Society of America. This collaborative spirit extended even to international counterparts in Europe, where Britain and France were developing their rival Concorde supersonic airliner. Despite the competitive nature of the aerospace industry and Cold War tensions, researchers on both sides of the Atlantic shared findings, compared results, and built upon each other's work. The supersonic transport represented a convergence of post-war optimism, Cold War competition, and genuine technological achievement. In the years following World War II, aviation had transformed from a novelty into an essential component of modern life. Jet airliners like the Boeing 707 and Douglas DC-8 had cut transatlantic flight times by more than half compared to propeller-driven aircraft. The question that captivated aerospace engineers and government planners alike was deceptively simple: why stop there? If an aircraft could cruise at twice or 3 times the speed of sound, it could slash flight times even further, making the world smaller and bringing distant continents within reach of a same-day journey. New York to London in under 3 hours. Los Angeles to Tokyo in 5. The economic and strategic implications seemed profound. Nations that mastered supersonic transport technology would command the skies of the future, dominating international travel and projecting their technological prowess across the globe. But designing a commercial aircraft has always required a delicate balance of competing factors. Engineers must consider cruising, landing, and takeoff speeds. They must calculate range and passenger or cargo capacity. They must account for weight with and without payload, for durability under stress, for comfort during long flights, and for safety under all conditions. And of course, they must always consider costs, both for manufacturing and for operations. Airlines, after all, needed these aircraft to turn a profit. Balancing these factors proved especially challenging with something as revolutionary as the SST. The American program envisioned an aircraft that would cruise at approximately Mach 3, 3 times the speed of sound, around 2,000 miles per hour. Yet this supersonic marvel would still need to take off and land at existing airports, using runways designed for much slower subsonic jets. It would need to operate safely in all weather conditions, carry hundreds of passengers in reasonable comfort, and do so at a cost that airlines could bear. Unlike with previous supersonic military aircraft, which operated in restricted airspace and answered only to military requirements, the civilian SST faced constraints that went far beyond pure engineering. NASA's scientists and engineers, along with their partners in industry, increasingly had to consider the environmental impacts of their designs. Engine noise around airports posed one concern, as supersonic aircraft required tremendous thrust, and their engines generated correspondingly tremendous noise during takeoff. The effects of high-altitude exhaust on the upper atmosphere represented another worry, especially regarding the little-understood ozone layer that shields Earth from harmful ultraviolet radiation. And then there was the sonic boom, the inevitable acoustic signature of supersonic flight. This phenomenon would prove to be perhaps the most intractable problem facing the SST program, a physical reality that no amount of political will or engineering cleverness could completely eliminate. The foundations of boom research. The National Advisory Committee for Aeronautics, NASA's predecessor organization, had built its reputation on methodical, practical research into aeronautical problems. Since its founding in 1915, NACA had relied heavily on ever more powerful and inventive wind tunnels to advance aviation technology. These wind tunnels became true national treasures, instruments that allowed researchers to test new designs, verify theories, and push the boundaries of flight without the expense and risk of full-scale flight testing. The value of wind tunnels lay in their flexibility and precision. They served as logical and adaptable instruments, useful for theoretical explorations as well as highly applied studies. More crucially, these tunnels allowed researchers to move fluidly back and forth between mathematical models and flight data, increasing the reliability of their models while also serving to predict aircraft performance. This iterative process of hypothesis, testing, and refinement had driven countless aeronautical advances. These wind tunnels remained just as essential during the early years of NASA, especially in helping design supersonic and hypersonic vehicles. The organization operated facilities ranging from small, bench-scale tunnels for basic research to enormous installations capable of testing full-scale components at realistic flight conditions. Each facility specialized in particular flight regimes or types of testing, creating a comprehensive network of research capabilities. Among the most important of these research centers was the Langley Research Center in Hampton, Virginia. Langley had been NACA's first field center, established in 1917, and it remained at the forefront of aeronautical research throughout the jet age and into the space age. The center's wind tunnels, laboratories, and skilled personnel would prove indispensable to understanding and potentially controlling sonic booms. The work concentrated at Langley drew on a small but dedicated group of researchers who would become the nation's premier experts on sonic boom phenomena. Harvey Hubbard led the noise reduction section of Langley's aeronautics division. A thoughtful and methodical scientist, Hubbard recognized early on that sonic booms represented a fundamentally new challenge in aeroacoustics. Harry Carlson, working in the same division, brought a talent for both theoretical analysis and practical experimentation. and Dominic Maglieri, a young engineer who joined Langley in 1951 fresh from the University of Pittsburgh with a degree in mechanical engineering, would dedicate his entire career to understanding sonic booms. These three men formed the core of NASA's sonic boom research effort, though many others would contribute significantly. Carlson tended to focus on wind tunnel experiments and the theoretical underpinnings of boom generation. Hubbard and Maglieri specialized in planning and monitoring field tests, recording data, and analyzing the mountains of measurements that accumulated from actual supersonic flights. Together, they pioneered the systematic scientific study of a phenomenon that had been little more than a military nuisance before the prospect of supersonic commercial aviation made it a matter of national importance. The theoretical foundations for understanding sonic booms had been laid by British mathematicians and physicists in the 1950s. G.B. Whittam, working at the University of Manchester, published groundbreaking analyses in 1952 that described how shock waves form and propagate from supersonic projectiles. Whittam's work introduced what became known as the F function, a mathematical tool that related the shape and volume distribution of an aircraft to the pressure signature it would create on the ground. F. Walkden, working at the College of Aeronautics at Cranfield, extended Whittam's work to account for the effects of lift. While Whittam's initial analyses focused primarily on the shock waves generated by an aircraft's volume displacing air, Walkden recognized that the lift required to keep an aircraft aloft also contributed significantly to the shock wave pattern. His 1958 paper on the shock pattern of a wing-body combination far from the flight path provided crucial insights into how these two effects combined. These theoretical frameworks divided the space around a supersonic aircraft into distinct regions, each requiring different analytical approaches. The near field, extending just a few body lengths from the aircraft, was where multiple shock waves generated by different parts of the airframe existed as separate disturbances. Wind tunnel models could provide fairly accurate measurements in this region, as the shock waves had not yet travelled far enough to fully evolve. The midfield represented the transition zone where these separate shock waves began to coalesce and strengthen. The processes governing this region involved complex nonlinear effects that made prediction difficult. Finally, the far field extended from several hundred body lengths out to the ground and beyond. By the time shock waves reached the far field, they had typically coalesced into the characteristic N-shaped pressure signature of a sonic boom, a sharp positive pressure spike as the bow shock arrives, followed by a gradual decrease through ambient pressure, and below, then a second sharp positive spike as the tail shock passes. Understanding how shock waves evolved from the near field through the midfield to the far field became one of the central challenges of sonic boom research. Wind tunnel testing could directly measure near-field conditions, but extrapolating these measurements to predict far-field effects required sophisticated mathematical models and, increasingly, computational power. The first systematic wind tunnel experiments on sonic boom generation took place in 1959, conducted by Harry Carlson at Langley. Working with the centre's 4x4-foot supersonic wind tunnel, Carlson tested 7 models of various geometrical and airplane-like shapes at different angles of attack. The tunnel's relatively limited interior space demanded the construction of extremely small models to obtain useful shockwave signatures. For measuring shockwaves at 8 body lengths distance, models needed to be about 2 inches in length. For attempting measurements at 32 body lengths, approaching far-field conditions, models had to be just 3/4 of an inch long. The precision required for fabricating these tiny models pushed the limits of manufacturing capabilities. Each had to be machined to tolerances of a few thousandths of an inch to ensure that measured shockwaves reflected the intended design rather than manufacturing imperfections. The models also needed to be mounted on support structures, called stings, that inevitably created their own shockwaves and could distort measurements, especially of the tail shock. Many of Carlson's initial models consisted of simple bodies of revolution, essentially streamlined projectiles with circular cross-sections. These forms were easier to analyze mathematically, and their shockwave patterns were better understood than those from more complex shapes. Using the area rule, a principle that Whitcomb had developed at Langley in the 1950s for transonic aircraft, these simple shapes could serve as equivalents for more complex aircraft configurations. The area rule recognized that for certain purposes, an aircraft's actual three-dimensional shape could be treated as equivalent to a body of revolution with the same cross-sectional area distribution along its length. Testing at Mach 2.01, Carlson determined that these simple models could serve as suitable substitutes for more realistic, non-axisymmetrical airplane shapes in obtaining theoretical estimates of far-field bow shock pressures. His results correlated well with existing theory, confirming predictions derived from Whitcomb's formulas on volume-induced overpressures and Walkden's work on lift-induced effects. Carlson even attempted to design one model with a shape intended to alleviate the strength of the bow shock, though this early experiment in boom minimization proved unsuccessful. Nevertheless, it represented NASA's first systematic attempt to explore whether aircraft shaping could reduce sonic boom intensity. In April 1959, before results from either Carlson's wind tunnel work or the first flight tests at Wallops Island had been published, Carlson and Maglieri provided early advice about sonic boom implications for the emerging supersonic commercial air transport program. Based on existing theory, some US Air Force and British reports, and preliminary findings from their own experiments, they reached a sobering conclusion. For the proposed supersonic transport airplanes of the future, booms on the ground would most probably be experienced during the major portion of the flight plan. The boom pressures would be most severe during the climb and descent phases of the flight plan. They warned that sonic booms during cruise would extend laterally for many miles on either side of the flight path, creating what came to be known as a boom carpet. The width of this carpet depended on altitude, with higher flight producing wider carpets but potentially weaker booms at any given point. The hope was that special operating procedures and high altitudes could help alleviate both problems to some extent, though the fundamental physics imposed limits on what could be achieved. The extreme precision demanded in making the tiny models needed for early sonic boom experiments, combined with the disruptive effects of mounting stings, vibration, limited sensitivity of pressure sensors, and interactions with tunnel walls, all conspired to limit a wind tunnel's ability to measure the type of shock waves that would actually reach the ground from a full-sized aircraft. This was especially true for something as large as the planned SST, which would be far bigger than any supersonic aircraft then flying. Even so, substantial progress continued throughout the early 1960s, and the data served as useful cross-checks on flight test data and mathematical formulas. In 1962, Harry Carlson used a 1-inch model of a B-58 Hustler bomber to make the first direct correlation between recent flight test data and wind tunnel results. The B-58, a sleek delta-wing bomber capable of sustained Mach 2 flight, had become one of the primary aircraft for sonic boom flight testing. Carlson's findings proved that wind tunnel readings, with appropriate analysis and scaling, could be used with reasonable confidence to estimate sonic boom signatures that would be produced by full-scale aircraft. This validation of wind tunnel techniques opened new possibilities for boom research. Instead of relying solely on expensive and sometimes dangerous flight tests, researchers could explore a wide range of aircraft configurations in the controlled environment of a wind tunnel. Several months after his B-58 validation study, Carlson concluded that locating the major portion of an SST's lift-generating surface aft of the maximum cross-sectional area could lower sonic boom overpressure. This principle would thereafter be considered in the design of most planned SST configurations. Exactly 5 years after publishing results of his first wind tunnel sonic boom experiment, Harry Carlson was able to report significant progress. In recent years, intensive research efforts treating all phases of the problem had served to provide a basic understanding of the sonic boom phenomenon. The theoretical studies by Whittam and Walkden had resulted in correlations with wind tunnel data and with flight data. A coherent framework was emerging that connected fundamental physics to measurable phenomena to practical aircraft design. As for the prospect of minimizing the strength of sonic booms, wind tunnel tests of SCAT models had revealed that some configurations produced lower overpressures than others. SCAT stood for Supersonic Commercial Air Transport, and NASA had been studying various SCAT configurations since the late 1950s. The arrow-wing design of the SCAT-15F, for instance, showed promise for reducing sonic boom while maintaining efficient cruise performance. The challenge, as always, was finding configurations that would reduce sonic booms without significantly sacrificing other needed attributes such as lift-to-drag ratio, stability, structural efficiency, or payload capacity. A major breakthrough in wind tunnel technique came in 1967 when Raymond Hicks and Joel Mendoza at Ames Research Center greatly improved the ability of wind tunnels to predict sonic boom characteristics. Experimenting with a 12-inch model of the XB-70 Valkyrie in the Ames 7x9-foot supersonic wind tunnel at Mach 1.8, they applied Whittam's near-field F-function theory in a new way. They compared pressure readings taken at one body length in the wind tunnel with actual flight test data from a real XB-70 at 4.5 body lengths and 290 body lengths from the aircraft. By carefully analysing how the near-field measurements related to far-field observations from the actual aircraft, they developed a new and more reliable method for extrapolating near-field F-function measurements to the far field. This advance allowed the use of much larger and therefore more accurate models for sonic boom wind tunnel testing. Instead of working with models barely larger than a finger, researchers could now use foot-long or even larger models and still obtain valid predictions of ground-level boom signatures. The mobilization of theoretical minds. Motivated by the SST and Concorde programs, scientists and engineers rapidly expanded knowledge and understanding of sonic boom theory during the 1960s. Much of their effort focused on ways to predict the sonic booms that various aircraft configurations would produce and how to modify these designs to lower the impact of shock waves reaching the surface. This goal became known as minimization or mitigation, and it attracted some of the era's most talented minds in aeronautics and applied mathematics. At the very start of the decade, when the British Aircraft Corporation was exploring options for a supersonic airliner, L.B. Jones, an aerodynamicist at English Electric Aviation, added to the fundamental understanding of sonic booms pioneered by Whittam and Walkden. Noting with characteristic British understatement that the sonic bangs caused by supersonic aircraft could be a nuisance, with a level of noise on the borderline of acceptable value, Jones introduced his theory by observing that it seemed important to examine ways of reducing them at the aircraft design stage. He presented equations for ways of lowering shock waves in the far field caused by lift, volume, and the combination of lift plus volume. Although his hypothetical designs were too blunt-nosed to be practical for high-speed flight, his work marked the first significant theory on how supersonic aircraft might be specifically designed to reduce boom intensity. Such possibilities were soon being explored by NASA aerodynamicists and a growing number of NASA partners in the American aerospace industry and university engineering departments. In addition to publishing results in technical reports and academic journals, researchers began presenting their findings at special conferences and professional symposia dealing with supersonic flight. One of the earliest such gatherings took place from September 17th to 1963, when NASA headquarters sponsored an SST feasibility studies review at the Langley Research Center. Attended by government, contractor and airline personnel, the conference examined every aspect of the planned SST program. In a session devoted to noise, Harry Carlson delivered a warning that would prove prophetic. Sonic boom considerations alone, he stated, might dictate allowable minimum altitudes along most of the flight path. In many cases, airframe sizing and engine selection might depend directly on sonic boom characteristics. The boom problem wasn't just an engineering challenge to be solved alongside others. It could fundamentally constrain the entire aircraft design. Harvey Hubbard and Dominic Maglieri discussed how atmospheric effects and community response to building vibrations might pose problems with the current SST sonic boom objectives. The FAA had set a desired goal of 2.0 pounds per square foot during the SST's acceleration phase and 1.5 pounds per square foot during cruise, hoping this would be acceptable to the average person exposed to the booms on the ground. But the more researchers learned about human perception of sonic booms and the physical effects on structures, the less certain they became that even these levels would prove acceptable for regular overland supersonic flight. The conference also discussed various other technological challenges for the planned American SST, some indirectly related to the sonic boom issue. Frictional heating from sustained supersonic flight posed significant materials challenges. An aircraft cruising at Mach 3 would experience skin temperatures exceeding 500 degrees Fahrenheit, hot enough to weaken aluminum, the primary structural material for subsonic aircraft. This meant an SST would need to be constructed largely from stainless steel, like the XB-70 bomber, or from titanium, like the still-secret A-12 and its variants being developed for the CIA and Air Force. Such construction would be dramatically more expensive than manufacturing a Mach 2.2 SST with aluminum skin, the approach being planned for the British-French Concorde. Britain and France had formally approved joint development of their supersonic transport on November 29, 1962, in an agreement that remarkably contained no provision for either side to back out. This would later prove significant as development costs spiraled and technical challenges mounted. The competing Concorde program added urgency to American efforts. If the Europeans succeeded in fielding the first operational supersonic airliner, American aerospace companies might find themselves shut out of what many assumed would be a lucrative market. Pan American World Airways, the most prestigious American airline, had already placed options on the Concorde, suggesting that American carriers wouldn't wait for an American SST if a European alternative became available first. Despite serious and potentially incurable problems raised at the NASA conference concerning cost and feasibility, the FAA had released its SST request for proposals on August 15, 1963, just before the conference. As explained by Langley's longtime supersonic expert F. Edward McLean, this changed NASA's role from having its own concepts evaluated by the airplane industry to one of evaluating the SST concepts of the airplane industry. NASA researchers would no longer be designing aircraft themselves, but would instead provide technical expertise to help government officials choose among competing contractor proposals. By January 1964, Boeing, Lockheed and North American had submitted initial proposals along with their jet engine partners. Boeing drew upon NASA's swing-wing SCAT-16 concept, proposing a sophisticated variable sweep design. Lockheed's proposal resembled the SCAT-17 with its canard foreplane and delta wing configuration. North American's design, which relied heavily on its XB-70 experience, but did not benefit as directly from NASA's SCAT studies, was soon eliminated from the competition. In retrospect, the manufacturers and government advocates of the SST were clearly hoping that technology would catch up with requirements before the aircraft went into production. The SST program schedule was too compressed, however, for many of the emerging concepts on controlling sonic booms to be incorporated or retrofitted into the contractor's designs. The imperative to beat Concorde into service drove decisions that prioritized schedule over technical maturity. As the program progressed, the sonic boom issue attracted growing attention from the broader scientific and academic community. The National Academy of Sciences formed a rather skeptical committee to study the problem between 1964 and 1965. Many scientists outside the aerospace community questioned whether exposing large populations to regular sonic booms was wise or even ethical. These concerns would only grow as more became known about the effects. By 1965, NASA specialists at Langley had been studying possible ways to address the sonic boom problem for 5 years. In June of that year, Ed McLean pointed out a potentially significant finding. Contrary to current asymptotic far-field theory, the near-field shockwaves from a transonically accelerating SST did not necessarily have to evolve into the final form of an N wave. This opened the prospect that a properly designed large supersonic aircraft flying at the right altitude might avoid projecting a full sonic boom to the surface. The insight stemmed from understanding how atmospheric properties affect shockwave propagation. In an idealized standard atmosphere, shockwaves from a supersonic aircraft would eventually coalesce into an N wave regardless of their initial configuration. But the real atmosphere isn't uniform. Temperature, pressure, humidity, and wind all vary with altitude and horizontal position. These variations cause shockwaves to refract, bend, and evolve in ways that might preserve some near-field characteristics all the way to the ground under certain conditions. This finding suggested that by carefully controlling aircraft configuration and flight profile, it might be possible to shape the sonic boom signature reaching the ground. Instead of the traditional sharp spikes N wave, a properly designed aircraft might produce a signature with multiple smaller shocks or with more gradual pressure rises. Whether such signatures would actually be perceived as quieter by people on the ground remained to be determined, but the theoretical possibility was tantalizing. Of major significance both at the time and even more potentially for the future, improved data reduction methods and numerical evaluations of sonic boom theory were being adapted for processing with new codes running on the latest International Business Machines computers. Langley used this computational capability for what was considered the first application of high-speed computers to the aerodynamic design of supersonic aircraft, representing a quantum leap in engineering analysis capability. Boeing developed one of the most widely known early sonic boom computer programs to help in designing its SST candidate. These automated data processing systems allowed faster and more precise correlations between wind tunnel and flight test data, leading to continued refinements in sonic boom theory. The predictions were still mainly applicable to bow shocks during steady and level flight in a standard atmosphere, but even these limitations represented enormous progress from just a few years earlier. Applying these new computational capabilities, Carlson, McLean, A. Warner Robins, and their colleagues at Langley designed the SCAT-15F, an improved SST concept with a highly swept arrow wing optimized for efficient cruise and, to some extent, a lower sonic boom. The design incorporated lessons learned from years of theoretical and experimental work. However, solving resultant problems with stability and control at low speeds proved more difficult. These solutions came too late for Boeing to adapt the SCAT-15F design for its SST in the late 1960s, but the lessons learned would prove valuable for future supersonic transport studies. The Acoustical Society of America, made up of professionals from all fields involving sound, ranging from music to audiology, and from noise control to vibration analysis, sponsored its first Sonic Boom Symposium on November 3, 1965, as part of its 70th meeting in St. Louis. McLean, Hubbard, Carlson, Maglieri, and other Langley experts presented papers on the background and techniques of sonic boom research as well as their latest findings. The paper by McLean and Barrett Shrout included details on the potential breakthrough of using near-field shockwaves to evaluate wind tunnel models for boom minimization. They described achieving a reduction in maximum overpressure in a climb profile from 2.2 pounds per square foot to 1.1 pounds per square foot through careful aircraft shaping. This technique also allowed for the use of 4-inch models, which were considerably easier to fabricate to the close tolerances required for accurate shockwave measurements than the tiny models used in earlier studies. Harry Carlson described how Langley Research Centre's latest high-speed computer programs for analyzing the lift and drag of aerodynamic configurations were being used by both NASA and the manufacturers to calculate F-function results and theoretical pressure signatures at various distances from the aircraft. These computational tools dramatically accelerated the design process, allowing engineers to evaluate dozens of configurations in the time it would have taken to build and test just a few wind tunnel models. Academic excellence joins the challenge. In addition to scientists and engineers employed by aircraft manufacturers, many eminent researchers in academia took on the challenge of discovering ways to minimize the sonic boom, usually with NASA's sponsorship and support. The influx of academic talent brought fresh perspectives and sophisticated mathematical techniques to the problem. Among the most influential was the team of Albert George and Richard Seabass at Cornell University, which had one of the nation's premier aeronautical laboratories. Seabass, already prominent in the field of aerospace engineering at just 29 years old, edited the proceedings of NASA's first Sonic Boom Research Conference, held on April 12, 1967. The meeting was chaired by Wallace Hayes of Princeton University, who was now devoting much of his attention to sonic boom mitigation. Hayes was well known for his groundbreaking work in supersonic and hypersonic aerodynamics. His 1947 dissertation, titled Linearized Supersonic Flow and written while at the California Institute of Technology, had in mathematical terms foreshadowed Whitcomb's area rule. Hayes brought to sonic boom research a deep understanding of the fundamental fluid dynamics governing supersonic flow. The 1967 conference was attended by more than 60 government, industry, and university experts in aeronautics and related fields. In reviewing the area rule as it applied to supersonic flight, Hayes offered a caution that cut to the heart of the boom minimization problem. The total equivalent source strength connected with the sonic boom could never be zero. Thus, the sonic boom below the aircraft was truly inescapable. The best that could be hoped for was that the boom would be a minimum for given values of weight, length, and altitude, with acceptable limits on drag. This sobering assessment reflected a growing realization among researchers that eliminating sonic booms was physically impossible for any aircraft large enough and heavy enough to serve as a practical airliner. The question wasn't whether an SST would produce a sonic boom, but rather how low that boom could be made, and whether the reduced boom would be acceptable to people on the ground. Boeing had been selected over Lockheed as the SST prime contractor less than 4 months before the 1967 conference. But public acceptance of even a reduced sonic boom was becoming recognized far and wide as a possibly fatal flaw for the program's future. The two most obvious theoretical ways to minimize sonic booms during supersonic cruise, flying much higher with no increase in weight, or building an airframe 50% longer at half the weight, were not considered realistic given the constraints of practical aviation. A presentation by Dominic Maglieri on flight test findings made apparent that even if an acceptably quiet cruise boom could be achieved, an SST would still have to deal with the problem of unpredictable, stronger booms caused by maneuvering accelerating, and atmospheric conditions. These so-called superbooms or focused booms could be dramatically louder than the normal N-wave signature, potentially exceeding acceptable levels even if the cruise boom itself was tolerable. The stated purpose of the 1967 conference was to determine whether all possible aerodynamic means of reducing sonic boom overpressure were being explored. Harry Carlson showed how various computer programs being used at Langley were complementing improved wind tunnel experiments for examining boom minimization concepts. Even minor changes in an aircraft's configuration could result in significant alterations of its shock waves. Wind tunnel comparisons of 4-inch models at Mach 1.4 confirmed that certain shapes could render a quieter flat-top signature for shock waves, albeit at a distance of only 5 body lengths from the model. Boeing sonic boom expert Edward Kane presented recent research on dealing with the tricky problems of atmospheric effects. The real atmosphere's variations in temperature, pressure, humidity, and wind could cause shock waves to focus, creating superbooms, or to defocus, creating shadow zones where boom intensity dropped below predicted levels. Understanding and predicting these effects was crucial for determining whether an SST could be operated safely over land. Albert George from Cornell explored the potential for reducing sonic boom overpressures, reaching the surface by designing airframes that could disperse some portion of shock waves caused by volume off to the sides of the flight path. This lateral dispersion of shockwave energy represented one approach to boom minimization that had received relatively little attention but might offer practical benefits. Notable aeronautics pioneer Adolf Busemann, now at the University of Colorado, expressed both frustration with the current situation and guarded hope for a solution. Busemann had fled Nazi Germany in the 1930s and become a towering figure in American supersonic aerodynamics. Since people were not satisfied with the sonic boom reduction that reasonable altitude for supersonic flights provided, naturally, he stated, further means for reductions must either be found or prove to be impossible. However, calling something impossible was dangerous. The times were full of innovations in physics and technology, and although certain laws of conservation were accepted as invariably valid, many scientists who had declared desirable effects impossible had been proved wrong. After all the papers were read and discussed, many attendees agreed that additional avenues of research were promising enough to be explored, but concerns remained about whether low enough sonic booms were possible using existing or foreseeable technologies. NASA's Office of Advanced Research and Technology, which hosted the conference, established specialized research programs on 7 aspects of sonic boom theory and mitigation at 5 American universities: Columbia, Colorado, Cornell, Princeton, and New York University, and at the Aeronautical Research Institute of Sweden. This mobilization of aeronautical brainpower almost immediately began to pay dividends. Seabass and Hayes co-chaired NASA's second Sonic Boom Conference from May 9th to 10, 1968. This came just weeks after Boeing replaced its variable sweep 2707 200 SST design, which had been found to be too heavy and mechanically complex, with the 2707 300, a delta wing configuration similar to Lockheed's losing proposal. The new design offered better structural efficiency, but less flexibility in optimizing performance across the full flight envelope from takeoff through supersonic cruise to landing. The conference included 19 papers on the latest boom-related testing, research, experimentation, and theory by specialists from NASA and participating universities. The advances made in just 1 year were impressive. In the area of theory, the fairly straightforward linear techniques for predicting the propagation of sonic booms from slender airplanes like the SST had proven reliable even for calculating some non-linear aspects of their signatures. Additional field testing had improved understanding of the geometrical acoustics caused by atmospheric conditions. Many papers, including those from Seabass, George, Hayes, McLean, and Carlson, presented promising aerodynamic techniques for reducing the strength of sonic booms. One of the most celebrated aerodynamicists recruited by NASA to work on the sonic boom problem was Antonio Ferri of New York University. An Italian Air Force officer and pioneer of supersonic research in pre-war Italy, Ferri had joined the anti-Nazi resistance movement after the collapse of the Mussolini regime and become a partisan leader before escaping in 1944 to the United States. There, he continued advancing high-speed research for NACA at Langley for several years before entering the academic world. At the conference, Ferri reported several innovative ideas on how to design a 300-foot SST airframe with reduced sonic booms by spreading lift along almost its entire length through suitable volume adjustments. Following these principles, he predicted, could yield maximum overpressures of about 1.0 pound per square foot while cruising at 60,000 feet, as compared to the 2.0 pounds per square foot expected with existing SST designs, without seriously hurting the aircraft's lift-to-drag ratio. This represented a significant improvement that might make the difference between public acceptance and rejection. Two papers presented at the 1968 conference would prove most significant to future progress, both dealing with new computer processing capabilities. Representing Aeronautical Research Associates of Princeton, Wallace Hayes reported on what became known as the ARAP program. Using the Fortran computer language, ubiquitous in scientific computing at the time, the program consisted of a master routine called Sonic, with 19 subroutines. NASA had sponsored this project to clarify confusion that existed among various complex numerical techniques being used for calculating the propagation of sonic boom signatures and comparisons with flight test measurements. Based on linear geometric acoustics, the ARAP program used F-function effects from a supersonic airframe at various Mach numbers and lift coefficients combined with acoustic ray tracing and an age variable to define, if not yet solve, the nonlinear effects that help shape sonic boom signatures. It was the first computer program with an algorithm comprehensive enough to accurately calculate a full range of overpressure signatures in a standard, horizontally stratified atmosphere with winds. This represented a major advance, allowing researchers to predict not just idealized boom signatures, but reasonably realistic ones, accounting for atmospheric effects. Using this tool, Hayes extended McLean's 1965 hypothesis on the persistence of near-field pressure signatures by showing that effects in the real atmosphere would tend to freeze the signature from supersonic aircraft at cruise altitudes before it reached the surface. Harvard Lomax of Ames Research Center offered a preview of a more distant digital future that would eventually be possible through the marriage of computational fluid dynamics, being pioneered at Ames with computer graphics. He reported preliminary results on using a cathode ray tube monitor directly connected to the core processor of a mainframe computer to show in real time the results of three-dimensional, nonlinear flow field analyses of a dozen diverse aircraft configurations in a search for lower boom signatures. After describing the mathematical principles involved, Lomax presciently predicted that the ability to compute flow fields for airplanes traveling at supersonic speeds with the aid of an immediate visual display of the calculations as they proceeded opened the possibility of devising new or revising parts of old numerical techniques. The full realization of this capability, with the development of supercomputers and massively parallel processors, would eventually prove to be the key to successful design of low-boom airplane configurations, though that achievement lay decades in the future. Despite these signs of considerable progress made by 1968, several important theoretical problems remained unresolved. Prediction of sonic boom signatures near a caustic, a region where acoustic rays converge and boom intensity can increase dramatically, represented a major objective that would require additional research and testing. The diffraction of shock waves into shadow zones, areas normally skipped over between primary and secondary sonic boom carpets, needed better understanding. Non-linear shockwave behavior near an aircraft remained somewhat mysterious, and the effects of turbulence on boom propagation and intensity were still somewhat mystifying. Ira Schwartz of NASA's Office of Advanced Research and Technology summed up the state of sonic boom minimization. It was yet too early to predict whether any of these design techniques would lead the way to development of a domestic SST that would be allowed to fly supersonic over land as well as over water. The technical challenges were being addressed with increasing sophistication, but the gap between theoretical possibilities and practical aircraft remained substantial. Operation Bongo and the Oklahoma City tests. The challenge to the SST posed by the sonic boom became even more serious shortly after the 1968 conference. In July 1968, President Lyndon Johnson signed into law a bill requiring the Federal Aviation Administrator to prescribe and amend such rules and regulations as he may find necessary to provide for the control and abatement of aircraft noise and sonic boom. Many expected this authority would effectively prohibit supersonic flight over land, as several other nations were already considering. But before any regulations could be written, policymakers needed data on how people actually reacted to regular sonic boom exposure. Previous tests had measured isolated booms or small numbers of booms over rural areas. No one had systematically studied what would happen if a substantial population were regularly exposed to the sonic booms an SST would produce. To fill this gap in knowledge, the FAA devised what would become one of the most controversial experiments in the history of American aviation. Oklahoma City presented an ideal location for such a test from the FAA's perspective. The metropolitan area had a population of about 500,000, large enough to provide statistically meaningful data, but not so large as to generate overwhelming opposition. The city had strong economic ties to aviation, with the FAA's Mike Mulroney Aeronautical Center providing employment and economic benefits. Tinker Air Force Base, one of the largest Air Force installations in the country, sat on the city's eastern edge. About 1 in 4 jobs in the area related to aircraft manufacturing or maintenance. More importantly, the city's residents were perceived to be relatively tolerant of aviation noise and sonic booms. They were accustomed to military jet operations from Tinker. They understood the economic importance of aviation to their community. When the FAA selected Oklahoma City for the tests, the local Chamber of Commerce threw a celebratory dinner. From the agency's perspective, if any American city could learn to live with regular sonic booms, surely it would be Oklahoma City. The experiment, officially known as Operation Bongo 2, began on February 3, 1964. The plan called for 8 sonic booms per day over a period of 6 months, from early morning through afternoon. Air Force F-104 fighters and B-58 bombers would produce the booms, with occasional contributions from F-101 and F-106 aircraft. The noise was limited to 1.0 to 1.5 pounds per square foot for the first 12 weeks, then increased to 1.5 to 2.0 pounds per square foot for the final 14 weeks. This range was about equal to what was expected from an SST cruising at altitude. Though 8 booms per day seemed harsh, the peak overpressures of 2.0 pounds per square foot were supposedly an order of magnitude lower than that needed to shatter glass and were considered marginally irritating according to published standards. The predictability and regularity of the booms was thought to help people adapt to them. An FAA-hired camera crew filming construction workers was surprised to find that the booms signaled their lunch break and the workers had simply incorporated them into their daily routine. The FAA rented 11 buildings in and around Oklahoma City, all outfitted with high-tech equipment for measuring the sonic booms. One home sitting directly under the flight path contained about $100,000 worth of recording instruments. Mobile van units were positioned throughout the city to capture data at various locations. The instrumentation measured not just boom intensity, but also building response, including vibrations and stresses that might lead to damage. Public opinion measurement was subcontracted to the National Opinion Research Center of the University of Chicago. Their task was to conduct surveys before, during, and after the test period to measure how residents' attitudes evolved with continued exposure. The hope was that even if people initially found the booms disturbing, they would adapt over time and come to accept them as a normal part of modern life. Initially, Oklahomans did seem to take the tests in stride. The regularity and predictability of the booms helped. People knew when to expect them and could time sensitive activities accordingly. The booms became a topic of conversation certainly, but not initially a source of widespread anger. Some residents even expressed pride in their city's contribution to advancing aviation technology. But as the weeks turned to months, and as the intensity increased during the second phase of testing, attitudes began to shift. The cumulative effect of 1,253 sonic booms over 6 months proved more wearing than anticipated. While many residents remained tolerant, a significant minority became increasingly upset. Dishes rattled in cupboards. Pictures fell from walls. Windows cracked. Plaster developed fissures. And the psychological impact of being repeatedly startled, even by expected sounds, began to take a toll. The claims for damages told a story of mounting frustration. There were 9,594 complaints of damage to buildings, 4,629 formal damage claims, and actual claims filed for a total of $12,845.32, mostly for broken glass and cracked plaster. To file a claim, residents had to fill out 18 pages of forms, including a 3-page explanation of how the government's sonic boom was the cause of the damage and not anything else. Witness testimony, certificates of ownership, and insurance information were among the other documents required. Many people probably didn't think the effort worth the trouble. The FAA's handling of these claims proved disastrous for public relations. The agency rejected 94% of all claims it received, ultimately paying out only about $123,000 in total. This cavalier dismissal of citizen complaints fueled a rising tide of anger that soared even after the experiment's conclusion. Although 73% of survey respondents said they could learn to live indefinitely with 8 sonic booms per day, that still left 27% saying they could not. With the city's population at 500,000, that 27% represented about 135,000 upset individuals. Senator Mike Mulroney, after whom the FAA's Aeronautical Center in Oklahoma City was named, had initially been a key supporter of the SST program. But by 1965, he had grown extremely upset over hundreds of letters from his constituents complaining about the FAA's treatment of their damage claims. He began demanding frequent reports from the agency. As late as May 1966, 2 years after the tests ended, the FAA was still attempting to respond to Mulroney's inquiries. The SST program lost all support from Mulroney, and his defection proved influential in Congress. The pressure put a premature end to the tests. On July 30, 1964, after 6 months and 1,253 booms, the experiments concluded. An Oklahoma City Times headline reported, "Silence is deafening." Zivko Angeluschev, a prominent hearing specialist serving with the National Academy of Sciences, recalled years later, I was witness to the fact that men were executing their brethren during 6 long months. With their thunder, the sonic boom, they were punishing all living creatures on Earth. The FAA attempted to spin the results positively. Their official report stressed that the overwhelming majority felt they could learn to live with the numbers and kinds of booms experienced. But this missed the point. Even if a majority could tolerate the booms, having a substantial minority strongly opposed would make regular supersonic overland flight politically untenable. And the negative publicity from the Oklahoma City tests influenced public opinion far beyond Oklahoma. The class action lawsuit filed by Oklahoma City residents against the US government wound its way through the courts. On March 8, 1969, the government lost its appeal. The message was clear. Exposing people to regular sonic booms against their will could carry legal as well as political consequences. After the tests, President Johnson's Presidential Advisory Committee transferred matters of sonic boom policy from the FAA to the National Academy of Sciences. Secretary of the Interior Stuart Udall complained that the Academy's committee did not include even one environmental preservationist. He pointed out that although the Oklahoma City tests had been designed in ways favourable to the SST, they were still extremely negative. By 1966, national grassroots campaigns against sonic booms were beginning to affect public policy. The Oklahoma City tests had been intended to demonstrate that Americans could adapt to regular sonic booms, paving the way for SST operations over land. Instead, they demonstrated that while some adaptation occurred, a significant portion of the population would remain opposed. The tests became a rallying point for SST opponents and provided concrete evidence of the problems sonic booms could cause. The experiment had backfired spectacularly. The XB-70 Valkyrie's contribution. While researchers worked on theories and conducted experiments, they also needed data from actual supersonic aircraft flying at the speeds, altitudes, and sizes relevant to the SST. The North American XB-70 Valkyrie provided an ideal platform for such research. Originally conceived in the 1950s as a Mach 3 strategic bomber, the XB-70 had been cancelled as a military program by 1961 due to vulnerability to surface-to-air missiles and competition from intercontinental ballistic missiles. But 2 prototypes were under construction, and they offered capabilities no other aircraft could match for SST research. The XB-70 was enormous, with a length of 196 feet and a wingspan of 105 feet. It weighed as much as 500,000 pounds fully loaded. 6 General Electric turbojet engines, each producing 30,000 pounds of thrust with afterburners, powered the delta-wing giant to speeds exceeding Mach 3 and altitudes above 70,000 feet. The outer wing panels could be folded down hydraulically from 0 to 65 degrees to improve stability at supersonic speeds and to allow the aircraft to ride its own shockwave, actually using the shock for additional lift. The aircraft was constructed primarily of brazed stainless steel honeycomb and titanium to withstand the intense frictional heating of sustained Mach 3 flight. These were the same materials being considered for the American SST, making the XB-70 an excellent testbed for understanding how such structures would behave under operational conditions. The Valkyrie was, in many ways, a flying laboratory for supersonic transport technology. NASA's Flight Research Center at Edwards Air Force Base had several SST studies underway during the early 1960s. Various aircraft had been pressed into service for different aspects of the research. A Douglas F-5D-1 was used for landing studies. A North American F-100C was modified to simulate SST handling qualities at lower speeds. A North American A-5, A Vigilante helped test air traffic control systems. A Lockheed Jetstar served as an in-flight SST simulator. but none of these aircraft could match the XB-70's combination of size, speed, altitude, and advanced materials. A joint agreement was signed between NASA and the Air Force to use the second XB-70A prototype for high-speed research flights in support of the SST program. This aircraft, designated AV-2, had better aerodynamics, improved inlet controls, and a superior instrument package compared to the first prototype. NASA research pilot Joe Walker, a legendary test pilot who had flown the X-15 rocket plane to the edge of space, was selected as project pilot. The research flights were to evaluate the aircraft on typical SST flight profiles and to study the problems of sonic booms on overland flights. The Valkyrie would fly at differing altitudes, Mach numbers, and weights over an instrumented test range at Edwards. NASA had set up extensive ground instrumentation to measure the boom carpet area and overpressure. 2 specially constructed housing units would allow researchers to study how booms affected residential structures. These plans went tragically awry on June 8, 1966. Major Carl Cross sat in the Valkyrie's cockpit for the first time, with veteran test pilot Al White in the pilot's seat. Their flight plan was straightforward: make several passes over recording instruments at Mach 1.4 and 32,000 feet for sonic boom data collection. Then, at the request of General Electric, they would fly in formation with 4 other GE-powered aircraft so photographers could take publicity pictures. The formation flight proceeded for about 30 minutes through some cumulus clouds. The aircraft maintained a racetrack pattern at 25,000 feet and 300 miles per hour. The XB-70, flanked by a NASA F-104N starfighter flown by Joe Walker, a Navy F-4B Phantom II, a T-38A Talon, and an F-104D photo aircraft with a Learjet flying nearby to capture the images. It was intended to be a simple publicity exercise showcasing General Electric's engine technology. On the final circuit, tragedy struck. For reasons never fully determined, Walker's F-104N moved slightly closer to the Valkyrie and then rose suddenly. The left tip of the starfighter's horizontal stabilizer touched the XB-70's drooped wingtip. The F-104 may have been further destabilized as it entered the XB-70's powerful wingtip vortex. In an instant, both aircraft were in catastrophic trouble. The starfighter flipped over and slammed into the Valkyrie's vertical stabilizers, destroying both vertical tails and part of the left wing. Walker, trapped in his disintegrating aircraft, had no chance. His F-104N exploded in a fireball. The mortally wounded XB-70 entered a flat spin, its crew compartment filling with smoke. Al White managed to eject in his escape capsule, but suffered serious injuries. Carl Cross, in the right seat, either could not eject or the ejection system failed. He perished when the Valkyrie impacted the desert floor. The loss of AV-2 and 2 pilots was a terrible blow. Beyond the human tragedy, more than $230 million in invested development costs disappeared in seconds. The sonic boom research that had been planned for AV-2, with its sophisticated instrumentation, would now have to rely solely on the first prototype. AV-1 had already proven to have directional stability problems above Mach 2.5, limiting its performance envelope. The first XB-70 was undergoing maintenance and modifications when its sister ship crashed. It did not fly again until November 3, 1966. Air Force Colonel Joe Cotton piloted it, while NASA research pilot Fitzhugh Fulton served as co-pilot. The flight reached a top speed of Mach 2.1. Between November 1966 and the end of January 1967, a total of 11 joint Air Force and NASA research flights occurred. These flights were made as part of the National Sonic Boom Program. The XB-70 flew at differing altitudes, Mach numbers, and weights over an instrumented test range at Edwards. The boom carpet area was determined and overpressure measured on the two specially constructed housing units positioned on the ground. The tests showed that a large aircraft such as the XB-70 at a high altitude produced sonic booms roughly as predicted by theory, though with variations due to atmospheric effects and aircraft maneuvering. More importantly, the tests demonstrated that high altitude did not automatically mean acceptably low boom intensity. One of the hopes for the SST had been that cruising at 60,000 to 70,000 feet would allow shock waves to dissipate and spread enough that ground-level overpressures would be minimal. The XB-70 data suggested this was overly optimistic. Even from extreme altitude, a large, heavy supersonic aircraft produced measurable and potentially disturbing sonic booms. The XB-70 research also provided valuable data on other issues facing SST designers. These included aircraft noise during takeoff and landing, operational problems related to sustained high-speed flight, control system design at various flight regimes, and comparison of wind tunnel predictions with actual flight data. The brutally hot supersonic environment revealed maintenance challenges and material behavior that would need to be addressed in any operational SST. The XB-70's last supersonic flight took place on December 17, 1968. On February 4, 1969, AV-1 took its final flight, a subsonic ferry mission from Edwards to Wright-Patterson Air Force Base in Ohio for permanent display at what is now the National Museum of the United States Air Force. The Valkyrie's research career had been brief, spanning just a few years of actual testing, but the data collected would inform supersonic transport studies for decades to come. The final years and growing opposition. Rather than conduct another sonic boom research conference in 1969, NASA deferred to a conference hosted by the North Atlantic Treaty Organization's Advisory Group for Aerospace Research and Development, held in Paris in May 1969. Experts from the United States and 5 other nations, including Britain and France, which were facing similar issues with the Concorde, attended this forum. 3 sessions and a roundtable dealt specifically with the status of boom research and the challenges ahead. The international nature of the conference underscored how sonic boom had become a global concern. The Concorde was approaching its first flight. The Soviet Union's Tu-144, a Concorde lookalike, had already flown. Japan was considering its own SST program. Wherever supersonic commercial aviation developed, sonic boom would be an issue. By October 1970, when NASA convened its 3rd Sonic Boom Research Conference in Washington, the American Supersonic Transport Program had less than 6 months left to live. The 150 scientists and engineers who gathered understood that they were witnessing the end of an era. The 29 papers presented at this conference, along with papers at the Acoustical Society of America's 2nd Sonic Boom Symposium in Houston the following month, might be considered collectively a final status report on sonic boom research during the SST decade. The reports covered the full range of topics related to the nature, measurement, and mitigation of sonic booms. Aircraft maneuvers, sonic boom minimization, simulation techniques and devices, as well as human, structural, and other responses to sonic booms, received detailed attention. The geometry and boom characteristics of various low boom concepts, both large civil transports and smaller business jet concepts, were discussed. Of future, if not immediate significance, NASA and its partners were making considerable progress in understanding how to design airplanes that could fly faster than sound while leaving behind a gentler sonic footprint. As Ira Schwartz summarized, in the area of boom minimization, the NASA program has utilized the combined talents of researchers at NASA Langley Research Center, Princeton University, Cornell University, and New York University to determine the optimum equivalent bodies of revolution that minimize overpressure, shock pressure rise, and impulse for given aircraft weight, length, Mach number, and altitude of operation. Research efforts have provided indications of how real aircraft can be designed to provide values approaching these optimums. This research must be continued or even expanded if practical supersonic transports with minimum and acceptable sonic boom characteristics are to be built. Any consensus among attendees about the progress being made on the sonic boom issue was tempered by awareness of the financial problems plaguing Boeing and the political difficulties facing President Richard Nixon's administration in continuing to subsidize the American SST. Many attendees seemed resigned to the reality that Boeing's final 2707 300 design, with its 306-foot length and planned 64,000-foot cruising altitude, would never come close to passing the overland sonic boom criteria being proposed by the FAA. Although the noise level ultimately deemed acceptable by the public remained uncertain, the consensus was that an N-wave signature from an acceptable SST must be reduced to at least 1.0 pound per square foot to allow cruising at supersonic speeds over the United States. Antonio Ferri lamented that programs for the first generation of these airplanes had been initiated without a complete understanding of the effects of the sonic boom on the population and their reaction against it. For designing the next generation of large supersonic transports, Ferri offered several concepts developed since the last conference, including an imaginative biplane configuration, as well as operational techniques and flight profiles to reduce overpressures to suitable levels. These proposals were ingenious, but underscored how far removed practical SST design remained from sonic boom acceptability. The shock waves from cruising at low supersonic speed, up to about 840 miles per hour at the right altitude, could under proper conditions either refract away from the surface or not coalesce enough to cause a full sonic boom. This condition, known as Mach cutoff, offered some hope that carefully planned operations while overland might still make an SST economically practical. However, this would require solutions to issues associated with meteorological conditions, topographical effects, building vibrations, caustics, and super booms. Albert George and his graduate student Kenneth Plotkin substantiated much about the complex relationship between turbulence and shockwave scattering, as well as N-wave distortions. This work was further refined by researchers at Columbia University, examining multiple scattering of shockwaves in a turbulent atmosphere. George had reported earlier on how reducing both tail shock and bow shock through careful design could lower the minimum achievable sonic booms well below levels calculated by earlier researchers. Thanks to new computer capabilities, Richard Seabass reported on progress in using linear equations to study the nonlinear characteristics of shockwaves at a caustic through automated numerical analysis and graphical representation. Much more study and testing would be needed, however, to make the quantitative predictions of sonic boom intensities required for even transonic civilian flight. In view of such unresolved technical issues, as well as overriding political and economic factors, Seabass generally echoed Ferri's opinion. We should adopt the view, he stated, that the first few generations of supersonic transport aircraft, if they are built at all, will be limited to supersonic flight over oceanic and polar regions. In view of such concerns, some attendees were even looking toward a more distant future when hypersonic aerospace vehicles might be able to cruise high enough to leave only an acceptable boom carpet at the surface. Regarding ongoing and future technological challenges, Lynn Hunton of Ames Research Center warned that with regard to experimental problems in sonic boom research, it is essential that the techniques and assumptions used be continuously questioned as a requisite for assuring maximum reliability. Harry Carlson probably expressed the general opinion of NASA's aerodynamicists when he cautioned that the problem of sonic boom minimization through airplane shaping was inseparable from the problems of optimization of aerodynamic efficiency, propulsion efficiency, and structural weight. In fact, if great care was not taken in applying sonic boom design principles, the whole purpose could be defeated by performance degradation, weight penalties, and a myriad of other practical considerations. Opposition to the SST grew rapidly in the late 1960s, becoming a cause célèbre for the emerging environmental movement, as well as a target for small government conservatives opposed to federal subsidies. The program faced criticism from multiple directions. Environmentalists worried about ozone depletion from high-altitude engine emissions and noise pollution from sonic booms. Fiscal conservatives objected to government funding of what many saw as a commercial venture that should be financed privately. Some scientists questioned whether the technology was mature enough for safe operation. The New York Times published its first strongly anti-sonic boom editorial in June 1968, linking the SST's potential sounds with an embarrassing incident when an F-105 flyover shattered 200 windows at the Air Force Academy, injuring a dozen people. Influential voices in media, academia, and politics increasingly questioned whether Americans wanted or needed supersonic commercial aviation badly enough to accept its drawbacks. The next 2 years brought a swelling crescendo of complaints about the supersonic transport. Economic analyses suggested the aircraft would be far more expensive to operate than initially projected. Airline executives, who had to consider actual operating costs rather than technological prestige, grew increasingly skeptical about the SST's viability. Pan American and other airlines that had placed options on the Concorde began reassessing their commitment as the true costs became apparent. By early 1971, the Boeing 2707 program was in serious trouble. The variable sweep wing design had proven too heavy and mechanically complex. The replacement delta wing design addressed some problems but created others. Development costs had soared far beyond initial estimates, and crucially, no one had found a way to make the sonic boom acceptable for regular overland flight. In March 1971, both the US House of Representatives and US Senate voted to discontinue SST funding. A joint conference committee confirmed the program's termination in May. In view of the SST's technical, operational, political, and economic hurdles, lowering its sonic boom in time for the final Boeing 2707, 300 design probably would not have been enough to save the program. The sonic boom issue had become emblematic of broader concerns about the SST, but it was not the only factor leading to cancellation. Nevertheless, the failure to solve the boom problem meant that even if all other issues had been resolved, the SST would still have faced severe operational restrictions. A decade's worth of progress. The cancellation of the SST and related cuts in supersonic research inevitably slowed momentum for dealing with sonic booms. Even so, the program, which had invested approximately $1 billion in supersonic research, left behind a wealth of data and discoveries. As documented evidence of this effort, the Langley Research Center alone produced or sponsored more than 200 technical publications on sonic booms over a span of 19 years, most related to the SST program. Many publications in the early 1970s were based on SST-related research and testing conducted earlier. This literature would prove to be of enduring value. Thanks mostly to the SST program, tremendous progress had been made in understanding and applying sonic boom theory at speeds up to Mach 3. Using the latest algorithms and geometric techniques, experts could now predict the evolution of a sonic boom signature from its shock pattern near an aircraft configuration to the surface. This could be done either by extrapolating measurements from several body lengths away in a supersonic wind tunnel model, or by using Whittam's F function as calculated from the volume and lift distribution of the aircraft. By using acoustic ray tracing and other techniques, sonic boom theory could account for the effects of variations in temperature, humidity, winds, and turbulence on sonic boom strength and behavior. It could even predict the approximate location of focused superbooms, though the precision of these predictions remained limited by the complexity of atmospheric phenomena. As for the need to mitigate sonic booms, the research of the SST era pointed toward the avenues to be followed in the future. Flying careful profiles at speeds of about Mach 1.15 could avoid creating sonic booms on the surface through a phenomenon known as Mach cutoff. But this probably would not provide enough speed advantage over conventional subsonic airliners unless most of a supersonic airplane's route could be flown at much faster speeds. For cruising at higher Mach numbers, it had become apparent that lowering sonic booms to acceptable levels would require either a reduction in a bow shock's overpressure or an increase in its rise time, making the initial spike in pressure less steep and sudden. The latter solution was deemed impractical since extending and smoothing out the N-wave to lengthen rise time would require an extremely long airplane, something impractical for a commercial transport. Also, as indicated by XB-70 tests and other human response data, this proposed solution would not necessarily help reduce annoying indoor vibrations caused by sonic booms. Some experts, particularly George and Seabass, proposed that these vibrations were the result of a sonic boom's impulse, a measure of the total momentum that a sonic boom signature could impart to a building. Buildings tend to vibrate at low frequencies, below the range of human hearing, in response to the relatively gradual pressure changes between the bow shock and tail shock. Reducing overpressure, which could be predicted based on an aircraft's Mach number, length, weight, altitude, and equivalent area distribution, therefore seemed to be the most feasible solution. As pointed out in numerous studies, the two basic ways of doing so were to lighten aircraft weight, thereby decreasing its need for boom-producing lift, and to specially shape an airframe to modify its shock waves, such as by creating a flat-top signature. The challenges lay in knowing exactly how to design such an airframe and knowing what level of overpressure would be acceptable to the general public. In May 1971, the same month that the House Senate Conference Committee terminated the American SST program, Albert George and Richard Seabass completed a short but extremely influential treatise on sonic boom minimization theory. Published in the AIAA Journal that October under the descriptive title Sonic Boom Minimization, including both front and rear shocks, its compact presentation of equations and graphs analyzed the parametric relations of shock waves to lift and area distribution as they affect the full sonic boom signature. Their findings offered the prospect of designing aircraft not only for controlling abrupt pressure rises to achieve what they referred to as a bangless boom, but also for possibly reducing the vibrations that annoyed people indoors. Future psychoacoustical studies would show that this outcome would indeed seem significantly quieter than the normal N-wave signature. Efforts during the coming decades to design supersonic aircraft that could reshape the sonic boom would cite the George Seabass minimization theory as a cornerstone of low-boom aircraft design. To help alleviate sonic booms, one futuristic idea that received some attention was the projection of a heat or force field to create a long phantom body in front and rear of the fuselage for eliminating troublesome shock waves. Although not quite physically impossible, aerodynamic issues as well as enormous power requirements and the additional weight made this proposal exceedingly unrealistic. It represented the kind of speculative thinking common in the late 1960s when anything seemed possible, but it was never a serious candidate for practical implementation. Several types of simulators, both large and small, proved useful in studying the physical and psychoacoustic effects of sonic booms. The smallest and least expensive was a spark discharge system. Langley and other laboratories used these bench-type devices for basic research into the physics of pressure waves. These systems created miniature sonic booms by using parabolic or two-dimensional mirrors to focus shock waves caused by discharging high-voltage bolts of electricity between tungsten electrodes toward precisely placed microphones. For studying effects of temperature gradients on boom propagation, Langley used a ballistic range consisting of a helium gas launcher that shot miniature projectiles at constant Mach numbers through a partially enclosed chamber. The atmosphere inside could be heated to ensure a stable environment for accuracy in boom measurements. Innovative NASA-sponsored simulators included a shock expansion tube mounted on a trailer and explosive gas-filled envelopes suspended above sensors at Langley's sonic boom simulation range. Other simulators were devised to handle both human and structural response to sonic booms. Unlike studies using actual sonic booms created by aircraft, these devices had the advantages of a controlled laboratory environment. They allowed researchers to produce multiple boom signatures of varying shapes, pressures, and durations as often as needed at relatively low cost. Langley's low-frequency noise facility, built earlier in the 1960s to generate the intense, eardrum-splitting sounds of giant Saturn boosters during Apollo launches, also performed informative sonic boom simulation experiments. This was a large cylindrical test chamber, 24 feet in diameter and 21 feet long, that could accommodate people, small structures, and materials for testing. The facility's electro-hydraulically operated 14-foot piston was capable of producing low-frequency sound waves from 1 Hz to 50 Hz and sonic boom N waves from 0.5 pounds per square foot to 20 pounds per square foot at durations from 100 to 500 milliseconds. To provide an even more versatile system designed specifically for sonic boom research, NASA contracted with General Applied Sciences Laboratories of Long Island, New York, to develop an ideal simulator using a quick action valve and shock tube design. Antonio Ferri was president of GASL, which he had co-founded with the illustrious Theodore von Karman in 1956. Completed in 1969, this new simulator consisted of a high-speed flow valve that sent pressure wave bursts through a heavily reinforced 100-foot-long conical duct that expanded into an 8-by-8-foot test section. It could generate overpressures up to 10 pounds per square foot with durations from 50 to 500 milliseconds. Able to operate at less than a 1-minute interval between bursts, its sonic boom signatures proved very accurate and easy to control. Looking to the future, as the dust settled on the cancelled SST program and researchers took stock of what had been accomplished, a consensus emerged about what had been learned and what challenges remained. The decade of intensive sonic boom research had transformed the field from a collection of scattered observations and rough theories into a coherent scientific discipline. Researchers now understood the fundamental physics governing sonic boom generation, propagation, and perception. They had developed mathematical tools and computational methods for predicting boom characteristics. They had identified principles for aircraft design that could reduce boom intensity, but significant gaps remained between this accumulated knowledge and a practical supersonic airliner that could fly over land without generating unacceptable booms. The loudest booms that most researchers believed the public might tolerate, around 1 pound per square foot or slightly less, still required aircraft designs that stretched the boundaries of what was economically and operationally practical. A commercial transport optimized for minimum sonic boom might be too compromised in other performance areas to compete with conventional subsonic aircraft on cost per seat mile. The human factors remained somewhat uncertain as well. While researchers had collected considerable data on how people reacted to sonic booms in various contexts, The question of what constitutes an acceptable boom for regular exposure remained contentious. Cultural factors, individual differences, time of day, type of activity being performed, and many other variables influenced whether people found a given boom level tolerable. The Oklahoma City tests had shown that even booms within the originally targeted range generated significant opposition from a substantial minority of residents. Nevertheless, the foundation had been laid for future progress. When and if technology, economics, and political will aligned to make another attempt at supersonic commercial aviation, the research conducted during the SST era would provide an essential starting point. The theoretical frameworks developed by Whittam, Walkden, Jones, George, Seabass, Hayes, McLean, and others would guide future designs. The experimental techniques pioneered at Langley, Ames, and university laboratories would inform future testing. The computational methods, though primitive by later standards, pointed the way toward the sophisticated simulation capabilities that would eventually enable low-boom aircraft design. The story of sonic boom research during the SST era ultimately represents both achievement and frustration. The achievement lay in the remarkable progress made in understanding a complex phenomenon and developing strategies to mitigate it. The frustration stemmed from the reality that this understanding came too late and progressed too slowly to save the SST program that had motivated it. The research had been conducted in service of an aircraft that would never fly, at least not in American skies. Yet the knowledge gained was not wasted. The lessons learned about sonic boom would inform military aircraft design, helping to reduce the impact of supersonic training flights over populated areas. The theoretical insights would contribute to broader understanding of shockwave physics, applicable in many contexts beyond aviation. And crucially, the foundation laid during the 1960s would support a revival of interest in low-boom supersonic flight decades later, when new technologies and renewed political interest made the challenge worth pursuing again. The three-way partnership between NASA, Boeing, and the academic aeronautical community during the late 1960s had yielded new knowledge about sonic booms, as well as scientific and technological advances in exploring ways to deal with them. In addition to flight test and wind tunnel data, progress came from new experimental techniques, some quite ingenious, and from the emerging power of computational analysis. The researchers who dedicated years of their careers to understanding sonic booms remained convinced that solutions were possible. Dominic Maglieri, who would continue working on sonic boom problems for decades after the SST cancellation, maintained that properly designed aircraft could eventually fly supersonically over land without causing unacceptable disturbance. The theoretical work of George and Seabass suggested that shaped sonic boom signatures, with multiple smaller shocks rather than the traditional N wave, might be perceived as significantly quieter. Computer simulations by Lomax and others hinted at design approaches that might achieve these shaped signatures. But in the early 1970s, these remained theoretical possibilities rather than demonstrated realities. The computational power needed to fully explore the design space did not yet exist. The willingness to invest billions of dollars in developing another supersonic transport had evaporated. Environmental concerns about aircraft were growing, not receding. The political and economic climate had shifted decisively against the SST. The Concorde would enter service in 1976, providing limited supersonic passenger service on routes over water. Its sonic boom prevented overland supersonic flight, restricting it primarily to transatlantic routes. The aircraft never achieved commercial success, with only 20 production aircraft built and only 2 airlines, British Airways and Air France, operating them. High operating costs, limited route networks, and small passenger capacity meant the Concorde served more as a prestige symbol than a practical transportation option. It would be retired in 2003 after a brief and ultimately unprofitable service life. The Soviet Tu-144, which bore a suspicious resemblance to the Concorde and flew just weeks before it, fared even worse. Technical problems plagued the aircraft throughout its brief operational life. A catastrophic crash at the 1973 Paris Air Show severely damaged the program's reputation. The Tu-144 flew only 55 passenger flights before being withdrawn from service. Like the Concorde, it proved that supersonic passenger flight was technically possible, but economically and operationally problematic. The American withdrawal from SST development left the field of supersonic commercial aviation to these European and Soviet programs, both of which ultimately failed to establish sustainable operations. The dream of routine supersonic travel, which had seemed so close to realization in the mid-1960s, receded into the future. Conventional subsonic jet airliners continued to dominate commercial aviation, improving incrementally in efficiency, capacity, and economics, but not attempting to break the sound barrier. For those who had worked on the sonic boom problem during the SST era, the program's cancellation brought a mixture of disappointment and relief. Disappointment because years of dedicated effort had not resulted in the technological breakthrough they had hoped to achieve. Relief because the honest assessment of most researchers suggested that the problem had not been fully solved, and that proceeding with SST operations over land would have created significant social and political difficulties. The question of whether sonic booms could be made acceptable would remain unanswered for decades. Not until the early 21st century would advances in computational fluid dynamics, combined with renewed interest in supersonic business jets and the emergence of new aerospace companies, bring the sonic boom problem back to the forefront of aeronautical research. The shaped sonic boom demonstration in 2003 using a modified F-5E fighter would finally prove experimentally what George, Seabass and others had predicted theoretically, that aircraft shape could fundamentally alter the sonic boom signature. This demonstration opened the possibility that a new generation of supersonic aircraft might indeed be able to fly over land without generating the traditional startling double boom. NASA's X-59 Quest program, decades in the future from the SST era, would attempt to prove that a piloted aircraft could produce a sonic thump rather than a sonic boom, quiet enough to potentially gain regulatory approval for overland supersonic flight. But that renewed effort would build directly on the foundation laid during the SST decade. The theoretical frameworks, experimental techniques, understanding of atmospheric effects, and insights into aircraft shaping that emerged from 1960s research would inform every subsequent attempt to address the sonic boom challenge. The hundreds of technical reports, the thousands of hours of flight testing, the millions of dollars invested in wind tunnels and simulators, and the countless hours of analysis and calculation had not been wasted. They had created a body of knowledge that would endure and prove valuable whenever humanity chose to once again pursue the dream of faster-than-sound passenger flight. The legacy of sonic boom research during the SST era extends beyond aviation. It represents a case study in how scientific research progresses, how technology development interacts with social and political factors, and how ambitious programs can generate valuable knowledge even when they fail to achieve their primary objectives. The sonic boom problem demonstrated that some technical challenges are not merely difficult but may be fundamentally constrained by physics in ways that cannot be overcome by sheer determination or increased funding. The SST program and its sonic boom research also highlighted the importance of considering public acceptance in technology development. No matter how impressive the engineering achievement, no matter how advanced the technology, if people do not want it in their daily lives, it will not succeed. The Oklahoma City tests taught a lesson about the limits of adaptation. While some people could learn to tolerate regular sonic booms, a substantial fraction could not or would not, and their opposition was enough to doom the program. This lesson about social acceptance of technology has resonated through subsequent debates about everything from nuclear power to genetic engineering to autonomous vehicles. Technological possibility does not guarantee social acceptability. Understanding this distinction and incorporating public values into technology development from the beginning rather than as an afterthought represents one of the enduring lessons from the SST era. The sonic boom research of the 1960s stands as a testament to what can be accomplished when talented people focus their efforts on a difficult problem. Within less than a decade, researchers transformed sonic boom from a mysterious and poorly understood phenomenon into something that could be predicted, measured, and potentially controlled. They developed theoretical frameworks that remain valid today. They created experimental techniques still used in modified form. They established principles of aircraft design that inform current low-boom research. That this knowledge did not immediately result in operational supersonic transports flying over American cities does not diminish the achievement. Science often progresses in fits and starts, with insights gained in one era lying dormant until changing circumstances make them relevant again. The sonic boom research of the SST decade planted seeds that would eventually bear fruit, even if that harvest came decades later than the original researchers had hoped. As NASA's researchers packed up their equipment after the final sonic boom conference in 1970, as Boeing dismantled the mock-up of the 2707 that would never be built, as universities redirected their talented graduate students toward other problems, the era of intensive sonic boom research came to an end. But the knowledge remained, preserved in technical reports, academic publications, and the memories of those who had participated in the great effort. That knowledge would wait, patient and ready, for the day when humanity would once again decide to challenge the sound barrier over land. The SST's sonic boom legacy is ultimately a story not of failure, but of foundation building. The researchers of the 1960s did not solve every problem, did not achieve every goal, did not make supersonic travel a routine reality. But they advanced human understanding, created tools and techniques that would prove valuable for decades, and established that the sonic boom, while inevitable for supersonic flight, need not be insurmountable. They showed that with sufficient knowledge, creativity, and effort, even the thundering boom could perhaps someday be tamed into something acceptable, allowing future generations to traverse the skies at supersonic speeds without leaving chaos in their wake. And so we come full circle, back to that particular kind of silence in the hours before dawn. The windows no longer rattle from passing sonic booms, at least not regularly over American soil. The skies have grown quieter in some ways, though paradoxically busier with subsonic traffic, but the dream endures, kept alive by the knowledge accumulated during those intense years of research, waiting for the moment when technology, economics, politics, and public will align to once again make possible the marvel of routine supersonic flight. When that day comes, if it comes, the sonic boom research of the SST era will provide the foundation upon which that dream can be built. If you enjoyed this deep dive into the history of sonic boom research and the ambitious supersonic transport program of the 1960s, please consider liking this video and subscribing to the Space Historian channel. We explore the fascinating intersections of aerospace technology, scientific progress, and human ambition, always with an eye toward understanding how we got to where we are today and where we might be headed tomorrow. Your support helps us continue creating detailed, thoroughly researched content about the most compelling stories in aviation and space history. Until next time, keep looking up, and remember that every thundering boom tells a story of human ambition pushing against the boundaries of the possible.